Hi students, welcome back to Civil Ed. I am Shiva Prasad from Civil Ed team. In our previous lecture video, that is friction lecture 2, we had solved problems on block friction. So in this video lecture, I shall present you numerical problems on ladder friction. For further topics in engineering mechanics, kindly subscribe to our channel Civil Ed. And now moving on to the problems on ladder friction, we shall the first problem. So the problem is like this: a ladder AB 3.5 meter in length and weight 250 Newton is placed against a wall with A at the floor level and B on the wall, AB making 60 degrees with the floor. The coefficient of friction between the wall and ladder is 0.25 and that between the floor and ladder is 0.3. In addition, it has to support a load of 1000 Newton at a distance of 3 meters from A along the ladder. To prevent slipping, a force P is applied horizontally at A at the level of the floor. Find the minimum force P required for this condition. Okay, so this is the question given and they have not given the sketch. So let's try to draw a sketch for this from the available data. So there is a ladder which is resting on the floor against a wall. A, the end of the ladder A is at the floor level and that in at the other end B is at the it is resting on the wall. The length of the ladder is given to be 3.5 meters and the ladder is inclined at 60 degrees with the floor. The weight of the, that is self weight of the ladder, is given to be 250 Newton. So this 250 Newton, that is self weight of the ladder, will be assumed to be acting at the CG of the ladder, that is center of gravity of the ladder. So we will place this 250 Newton, that is self weight of the ladder, exactly at the center of AB, that is 1.75 meters from A or from B. So 3.5 divided by 2, exactly at the center we are placing 250 Newton, that is self weight of the ladder. Next, moving on, some more information is given, that is coefficient of friction between the wall and ladder is given to be 0.25, that is between wall and the ladder, that is I am representing it by mu B, coefficient of friction mu, and at B mu B equal to 0.25, and that between the floor and the ladder is 0.3. so between the floor and the ladder the coefficient of friction is given to be 0.3. so in addition to it, it has to support a load of 1000 Newton 3 meter from A at a distance of 3 meter. Let us say we have to apply an external load, so that is 1000 Newton. So this is how we draw the sketch based on the given information. So that is the thing. And further what is asked: to prevent slipping, a force P is applied horizontally at A. So at A, a force P is applied, that's what they say, at the level of the floor. Find the minimum force P required for this condition. So they are asking the minimum force P required. So this ladder, due to the applied loads and its own self weight, it may have there may be a situation wherein it may slip due to the applied loads. So a force P has to be counteracted to stop the ladder from slipping. So what is that minimum force P required, for this particular condition? That's what they have asked in the question. So for this sketch, what we have drawn, we will try to draw the free body diagram also on the same sketch. So let's see what are all the things we need to consider for drawing the free body diagram. So already we have this self weight being acting at the center of AB, 250 Newton. Another applied load, that is another external load, 1000 Newton load is acting at a point 3 meter from A, so that is another force. So along with these things, we will have normal reactions at the contact points. So at A, let me call it as NA, which is perpendicular to the floor or the contact surface. Next at B, we have NB, again it is perpendicular to the contact surface, so I'll represent it by NB. So at A, the ladder may slip towards the left, that is on the ladder if it should slide on the floor, it will move towards the left. So my frictional force will be in the opposite direction to the impending motion. So I will just assume the direction of the frictional force at A, that is FA, to be rightwards. And coming to point B, the frictional force will be in the upside direction. Why? Because if A should slip and move forward on the floor, B has to come down. So the motion of the ladder point B will be coming down, and for this the frictional force will be in the upward direction, that is opposite to the impending motion. So I'll call it as FB. So another thing is the minimum force P required for this entire condition has been asked in the problem, so that also I will consider as the unknown force P, and that's what we are required to find. So this entire ladder problem, it's in the limiting friction condition, that is they have asked us to find the minimum force P to prevent slipping. So that means to say, if it is in the verge of sliding, what should be the minimum force to stop that ladder from sliding? So we say that this is the stage of motion impending. So at this stage we can consider the equation of limiting friction, that is maximum frictional force comes into picture, and that value will be equal to mu, that is coefficient of friction, multiplied by the normal reaction. This relation we will be using while solving this problem. So this is the thing. So let's begin to solve this problem. So considering the free body diagram of the ladder, so that's what we have got it just now, and applying the conditions of equilibrium. So what are all the conditions of equilibrium that we need to consider here? See, when we solve the problems on block friction, that is in the previous video, if you have observed the previous video, if you have not observed the previous video, please check out our previous videos wherein we have solved the problems on block friction. And in those problems, for drawing the free body diagrams, we had considered each block at a time and analyzed it as a concurrent force system. But now problems on ladder friction are analyzed by considering the entire ladder as a single force system. That is, this force system is considered to be a non-concurrent force system, because all these forces are at different places and they don't meet at a common point. So this is a case of non-concurrent force system. So let's just consider this as a non-concurrent force system, for which the conditions of equilibrium will be sigma V equal to 0, sigma H equal to 0, and sigma M about any point equal to 0. So these are the three conditions of equilibrium we will be using for any non-concurrent force system. So to begin with, the first condition of equilibrium, sigma V equal to 0. So the sign conventions would be upward positive and downward negative. So what are all the forces to be considered here in the vertical direction? Na, so acting upwards, plus Na, 250 Newton vertically downwards, minus 250, and 1000 Newton force acting downwards, minus 1000, and finally the frictional force Fb acting upwards, so plus Fb equal to 0. This is the equation for sigma V equal to 0. Then on substituting the value of Fb as 0.25 times Nb. What is 0.25? The coefficient of friction mu b equal to 0.25 and multiplied by the normal reaction Nb. So 0.25 Nb we are writing in place of Fb. So on further simplifying this equation, we get this equation: Na plus 0.25 Nb equal to 1250. So let's call it as equation number 1. Further moving on to second condition of equilibrium. So the sign conventions would be right side positive and left side forces considered negative. So right side forces plus P, so that is the required force to be found, so that is plus P, and plus Fa again right side, then minus Nb left side force, so equal to 0. So P plus Fa minus Nb equal to 0. On substituting for Fa with 0.3 Na, that is mu times Na minus Nb as it is equal to 0. So that we will call it as equation number 2. So with this we will move on to the third condition of equilibrium, that is applying moments at any point equal to 0. Third condition of equilibrium. So which point do I select? If you ask me, I'll select point A. Why? The reason is we have three unknowns here: Na, Fa and P. Anyhow, Fa you can convert in terms of Na, but still we will remain with two unknowns P and Na. But at B we have this Nb and Fb. Again Fb you can convert it in terms of Nb, and you will have only one unknown Nb at B. So what I'll do is I'll choose the moment center A, so that all these forces at A will not be coming into picture at all. So I'll choose moment center A and I'll apply moments, that is sigma m about A equal to 0. So let's begin with applying the moments, for which I require the perpendicular distances of all the forces from the point A, that is moment center. So let me begin with that, identifying the perpendicular distances. Okay, the first force I'll consider 250 Newton force. So the line of action of 250 Newton force is this, and the perpendicular distance would be from A to the line of action of 250 Newton force. So that I get it by applying cos 60 degree for this triangle. Okay, please observe the movement of this pointer. So this small triangle, the hypotenuse length is 1.75 and cos 60 degree, so the adjacent length you will get 0.875 meters. Next, further 1000 Newton force, the line of action is from 1000 up till here. The line of action, just observe the line of action of 1000 Newton force. So the perpendicular distance would be from A to line of action. So this is the perpendicular distance between A and the line of action of 1000 Newton force. So this again I will consider the hypotenuse length 3 meters, and this right angled triangle will fetch me cos 60. By applying cos 60 I will get the adjacent length to be equal to 1.5 meters. That is nothing but the perpendicular distance between moment center A and line of action of 1000 Newton force. Next, further moving on to Fb force, line of action of Fb and distance between A and line of action of Fb will be obtained by applying again cos 60 for this entire bigger triangle, that is length of the hypotenuse length will be 3.5 meter hypotenuse, and the 60 degrees is the inclination. So this entire triangle, the adjacent length will be 1.75 meters. So that is nothing but the perpendicular distance between moment center A and the line of action of FB. So this one. So next, that is NB, force NB, the perpendicular distance between line of action of NB is like here. Just observe the pointer. Line of action of NB is this one, and the perpendicular distance would be from A to the line of action. So by applying sin 60, please observe here, by applying sin 60 for this entire triangle, I'll get this length. So that is nothing but equal to the required perpendicular distance between the line of action of NB and moment center A. So now I have all the distances. So that basic formula, moment is equal to magnitude of force into the perpendicular distance, that we will apply by considering a sign convention. So clockwise moments positive, anti-clockwise moments negative. So anti-clockwise negative. So let's use this sign convention and apply moments of all the forces about A. First force 250 is the magnitude of force into perpendicular distance 0.875 from A to line of action of 250 Newton force, 0.875, plus Y about A. If you move this force in its own direction, it will cause a clockwise rotation. Just observe the pointer, it is showing clockwise rotation. So clockwise moment, we are assuming it to be positive. 250 Newton force will produce clockwise rotation about moment center A. So plus 250 into 0.875. Next force 1000 Newton. 1000 Newton is the magnitude of the force, and the perpendicular distance between A and line of action of 1000 Newton force is 1.5 meters, and it is going to create a clockwise rotation. So clockwise rotation 1000 Newton force, so it is plus here 1000 into 1.5. Next FB. So FB about A, it is going to create a anti-clockwise rotation. See, just observe, anti-clockwise rotation FB is going to create about A. So minus FB into perpendicular distance 1.75, A to the line of action of FB 1.75. So minus FB into 1.75. Next, the last force NB, it is just move that force NB along its own direction, it is going to create anti-clockwise rotation about A. So NB minus NB into 3.03, that is the perpendicular distance. So this is the complete equation for sigma m about A equal to 0, that is the third condition of equilibrium. Let's simplify this equation. So substituting FB, in place of FB we substitute 0.25 NB. So that is the thing, and further only NB is the unknown in this equation. You get the value of NB to be equal to 495 Newton. So with this we get the equation, we get the value of NB to be equal to 495 Newtons. So this NB value, let's substitute in the previous equations, that is equation number 1. If we substitute, we get the value of NA. In equation number 1, if you substitute NB, you get the value of NA to be equal to 1126 newtons. Again substituting the values of both NA and NB in equation number 2. In equation number 2 you will get the value of P. That is the required force P to be applied, the minimum force P to be applied at A, at the level of the floor, to stop the ladder from sliding. So at the impending motion condition we have found the value of P to be equal to 157 Newton. So this completes the first problem on ladder friction. Let's move on to another numerical problem. So a ladder 5 meter long rests on the floor and vertical wall as shown in figure. The sketch is given to you. Coefficient of friction at the wall is 0.2. Yes, this is the thing. And at the floor is 0.4. Okay, at the floor mu A equal to 0.4. The weight of the ladder is 200 Newton, can be considered as acting at the center of gravity of the ladder. So exactly at the center of this AB length, 200 Newton force, that is self weight of the ladder, is assumed to be acting. The ladder supports an additional load of 900 Newton at C. So this is called as point C in the problem. So 900 Newton force, additional load, acts at 1 meter along the ladder from top. Okay, from point B, 1 meter distance, 900 Newton load, external load is acting. So determine the lowest value of angle between ladder and floor at which ladder may be placed without causing any slip. Okay, they have asked you to find the lowest angle between ladder and the floor. So that is angle theta you are required to find here. So they have asked the value of lowest angle theta. Lowest means as the point A moves away from the wall, theta works out to be minimum. So what is that largest distance at which A can be placed from the wall, or what might be the lowest angle? So as you go farther and farther as the point A moves farther and farther, that will be the lowest, the theta value keeps decreasing. So that angle they are asking, so which will prevent the ladder from slipping. So that minimum angle you are required to find. So with this information, so let's draw the free body diagram. So at the contact points I have NA and at B I have NB. Next, the frictional force at A. Okay, the impending motion ladder, if it is going to slip leftwards due to the applied loads, so definitely the frictional force should act in the opposite direction of the motion of the ladder AB. So the direction of the frictional force FA will be in the right side. So that is opposite to the direction of motion of ladder point A. Next, at B, what is the direction of friction? So FB would be acting upwards. Why? Because if the ladder point A moves towards the left, then B, the other end of the ladder point B, has to come down. So this downward motion of the ladder is prevented by upward frictional force FB, so upward direction. So this completes the free body diagram for this given problem. So now, considering this free body diagram of the ladder, let's apply the conditions of equilibrium. That is 3 conditions of equilibrium: sigma V equal to 0, sigma H equal to 0, and algebraic sum of moments about a given point equal to 0. First condition of equilibrium, sigma v equal to 0. Upward forces positive, downward forces negative are the sign convention that we are going to adopt here. So the equation would be plus NA, that is upward direction, plus NA, downward forces minus 200, minus 900. Next again FB plus FB because upward force, NA minus 200 minus 900 plus FB equal to 0. Further on simplifying by substituting FB to be equal to mu times NB, because it is a case of motion impending situation. So definitely we can use this limiting friction F equal to mu times N. So that's what we have done, substituted for FB here, and further simplifying this equation we get an equation NA plus 0.2 NB equal to 1100. So let's call this as equation number 1. So next condition of equilibrium, sigma h equal to 0, right side force positive, left side forces negative. So that is the sign convention what I am going to assume here. So the forces along the horizontal plus FA, right side force, plus minus NB, left side force, minus. So FA minus NB equal to 0. Next, further substituting for FA, that is mu is equal to 0.4 here. So 0.4 NA minus NB equal to 0. So what is this? Limiting friction condition. So this formula we have used here. So on simplifying we get NB equal to 0.4 NA. So let's substitute this value of NB in equation number 1 and we get the value of NA directly. So NA equal to 1018.52 newtons. So again substituting this value of NA in the equation of NB, we get 0.4 into NA will be equal to 407.5 newtons. Okay, so the value of NA equal to 1018.52 newtons and value of NB equal to 407.5 newtons we have found from two conditions of equilibrium. Next, with these two values of NA and NB, let's move on to the third condition of equilibrium, that is sigma m about A equal to 0. Again, why I choose A here? Because I have okay, you have same number of unknowns on both the cases at point A and point B. So you can apply the moments about any point. Okay, it's your wish, but I will consider the moments at about point A. So I'm choosing the moment center to be point A. So first step is to find all the perpendicular distances between moment center and the line of action of all the forces. So that I will do now. First, 200 Newton force, perpendicular distance between line of action and moment center A is this perpendicular distance. So how do I get that? I don't know theta now, so I'll express that in terms of theta itself. So applying cos theta to this triangle with hypotenuse 2.5 meter length, so the adjacent side measures 2.5 cos theta. I'll keep it in terms of cos theta only. So theta is the unknown here. I need to find that value only in this problem. Next, 900 Newton force. Line of action is along this line. So perpendicular distance between A and line of action of 900 Newton force would be 4 cos theta. 4 is the hypotenuse length here. Okay, so basics of trigonometry, nothing else. Next, force FB, line of action is this. Perpendicular distance between A and line of action would be, again by applying cos theta for this entire right angled triangle. Just observe the movement of the pointer here. So this entire triangle, so hypotenuse length 5 meters, so 5 cos theta is the adjacent length for this triangle. So I got these three. Next, one more force, NB. What is the perpendicular distance? So line of action of NB is this, and the perpendicular distance between the line of action and A is this length. This I would get by applying sin theta to this entire triangle. So by that I will get this wall length, that is nothing but equal to the perpendicular distance of the line between the perpendicular distance between line of action of NB and A. So that's value works out to be 5 sin theta by applying sin theta to this triangle, entire triangle A, B and this. Just observe the movement of the pointer, this triangle. Okay, for now I have found all the perpendicular distances between forces, the line of action of forces and moment center A. So let me apply the moments about A, that is third condition of equilibrium. For this, the sign conventions are clockwise moments positive and anti-clockwise negative. So the same sign convention let us consider. So 200 into 2.5 cos theta. So what is this? First force about A, 200 is the magnitude of the force and the perpendicular distance is 2.5 cos theta. So that is what I am going to write here, 200 into 2.5 cos theta. So why plus? Because 200, if you move it along its direction about the point A, it will create clockwise rotation. So it is plus. Next, second force, 900 Newton. Again this force 900 into perpendicular distance 4 cos theta from here to here, line of action. So 900 Newton force will also create clockwise rotation. So plus 900 into 4 cos theta. Next force, FB about A. See, just observe this direction of FB. It is moving up. Okay, so if you just make it to rotate along about A in the same direction of FB, so it will create a anti-clockwise rotation. So minus FB into 5 cos theta. 5 cos theta is the perpendicular distance between FB, line of action of FB and A. So minus, why minus? Because anti-clockwise rotation. Okay, so you understood this. Next, the last remaining force, NB. Again NB, if you move along its direction, it will create anti-clockwise rotation about moment center A. So NB is the magnitude of force multiplied by perpendicular distance 5 sin theta equal to 0. So this is the entire equation for the third condition of equilibrium, sigma m about A equal to 0. So let me try to simplify this equation by substituting for FB, limiting friction. So mu times F, that is 0.2 here, FB is equal to mu into NB. So 0.2 into 407.407 is the value of FB we have, value of NB we have found already. So NB is equal to 407.5. So approximate value is 407.5, that we are substituting here, into 5 cos theta minus NB, again we are substituting here, NB value 407 into 5 sin theta equal to 0. So this, on further simplification, we get this equation 3692.6 cos theta is equal to 2037 sin theta. So this is in terms of cos theta and sin theta, and further simplification we get tan theta equal to 1.813 and theta will be equal to tan inverse of this, which is equal to 61.12 degree. So this is the minimum angle of inclination that can be used for to avoid this ladder from slipping. So this is the minimum most angle. If you reduce the angle lower than this ladder will begin to slide. So that is what is the inference. So with this we completed 2 problems in ladder friction. So third problem is your assignment problem. So this is nothing but same as the first problem what we have solved in this video lecture. So the only change what I have done is find the maximum force P required for this condition. So that means to say, in the first problem what we have solved, they had asked for minimum force P required for this condition, for the given problem condition. But now I am asking you to solve for maximum force P required for this condition. So please solve this problem, and further in the upcoming videos I will be also solving the assignment problems for you people. So just don't forget to subscribe to our channel for in order to view and learn all the problems that are going to be taught by me in the upcoming videos. So please share with your friends and like, just click on like button, and further I wish you people to share with your friends so that it reaches the maximum engineering students strength. Okay, with this we have come to the end of this video lecture. In the upcoming videos, in the next video maybe we are going to solve problems on rope friction and wedge friction. Okay, thank you students.